To grasp our place in the universe, it helps to count in powers of 10. Moving from the scale of our bodies up to the distances between nearby stars requires a jump of 16 orders of magnitude. Because of this extreme distance, stars cannot be spatially resolved by telescopes. The physical sphere is reduced to a zero-dimensional point of light. Yet we can determine their surface temperatures, atomic makeup, wattage, and their exact physical radii. This gap in our knowledge is bridged entirely by deduction. We start with the only 3 raw pieces of data actually hitting our detectors on Earth. First, the star's coordinate position on the celestial sphere. Second, its apparent brightness, or flux, which is the total energy captured by our telescope mirrors over a given amount of time. And third, the color spectrum embedded within that incoming light. From these 3 isolated variables, we build a logical ladder. By systematically applying geometry, electromagnetism, and quantum thermodynamics, we can reconstruct the physical star. Astrophysics relies on mathematical inference. It is the mechanism we use to expand a mere point of light back into a fully realized 3-dimensional world. The first necessary step in this logical chain is determining the star's distance. Without knowing exactly how far away the light originated, we cannot calculate any of its absolute physical properties. To measure this, we use the Earth's orbit around the Sun. Observing a star 6 months apart provides a changing vantage point, creating a baseline of 2 astronomical units. By tracking how the target star shifts against background objects, we calculate the parallax angle. For massive interstellar distances, the trigonometry simplifies. The tangent of the angle collapses into a direct ratio between the baseline and the distance. This relationship defines the standard unit of astronomical distance. A parsec is simply the distance at which this parallax angle equals exactly 1 arcsecond. On Earth, atmospheric turbulence blurs the incoming light. This optical distortion restricts our ground-based parallax measurements to stars within roughly 100 parsecs of our solar system. To measure distances deeper into the galaxy, we launch observatories above the atmosphere to record these microscopic angular shifts in a vacuum. Securing the distance locks in our physical metric. It translates the 2-dimensional illusion of the night sky into measurable space. With the distance established, we can interpret the second piece of raw data, the star's apparent brightness. This determines its true intrinsic power, known as luminosity. Apparent brightness, or flux, is merely the amount of energy passing through a specific area of our detector. As a star's radiation travels outward through a vacuum, it spreads evenly and isotropically across an expanding sphere. The surface area of that sphere grows with the square of the distance. Because we now possess the distance, we run the inverse square law backward, multiplying the flux we capture on Earth by the total area of the sphere to calculate the absolute luminosity. This mathematical relationship, the distance modulus, separates how bright a star appears from its true absolute magnitude. We have taken a simple flux reading, applied a geometric distance, and calculated the exact wattage of a distant nuclear reactor. We know the star's energy output. To understand its physical structure, we now need to calculate the temperature of its surface. For this, we analyze the final Earth-bound observable, the color spectrum of the incoming light. This chart shows the spectral energy distribution for an idealized radiating object called a blackbody. The curves represent how energy is distributed across different wavelengths of light at specific temperatures. As the temperature of the gas increases, the peak of the emitted light shifts mathematically toward shorter, bluer wavelengths, immense telescope time. Astronomers use a pragmatic photometric workaround. Instead of scanning the entire curve, they pass the incoming light through a standardized set of filters, isolating the wavebands. Comparing the ratio of light captured in these specific bands provides a color index. Because of the predictable shape of the blackbody curve, this single ratio instantly yields the star's color temperature. The quantized energy levels of the incoming photons provide an exact thermometer for a surface trillions of miles away. With luminosity and surface temperature solved, the physical size of the star is heavily mathematically constrained. The relationship between these variables is dictated by the Stefan-Boltzmann law. The energy flux emitted from a surface area scales sharply with the fourth power of its temperature. The total luminosity is exactly equal to the star's surface area multiplied by this temperature flux. Since we have derived the luminosity and temperature, the only remaining unknown is the radius. To emit a specific total luminosity at a specific surface temperature, a star is required by the laws of physics to possess an exact surface area. Through the synthesis of thermodynamics and geometry, we have successfully extracted a concrete three-dimensional physical measurement. But stars are real physical objects, not perfect mathematical abstractions. A star consists of a hot interior surrounded by cooler, lower-density gas in its upper atmosphere. As light from the interior diffuses outward, atoms in this cooler layer absorb specific outgoing photons. Because atomic electrons transition between discrete energy levels, they absorb very specific wavelengths. These missing photons appear as dark gaps in the spectrum, providing an exact chemical barcode for the star's elemental composition, primarily hydrogen, helium, and traces of heavier metals. The star's surface temperature dictates which elements lose electrons to ionization, creating distinct spectral patterns. As the surface cools from type O down to type M, the absorption lines shift. Heavy ionization in hot stars gives way to intact atoms in cooler ones. These noisy deviations from our perfect mathematical models are exactly what give each star its unique chemical and structural identity. We began this process with almost nothing. A telescope provided only a position coordinate, a brightness level, and a raw smear of colored light. But observing the position shift mapped the geometry of distance. Distance and brightness revealed absolute luminosity. The color spectrum proved the temperature, and together, luminosity and temperature defined the physical radius and composition. This unbroken chain of reasoning is the bedrock of modern astrophysics, allowing us to map the mechanics of the galaxy without leaving Earth. Through the rigorous application of physical laws, a dimensionless point of light in a telescope is successfully expanded into a massive, structurally defined nuclear furnace.